In this example, we illustrate a nodal analysis with current sources. Let's look at this circuit. We have two current sources here, and we want to use nodal analysis to find current IS here. So there are a few steps to apply nodal analysis. Step 1, we want to find a reference node. The reference node normally is chosen at the bottom of the circuit just for convenience. In this case, I choose this node as a reference. Next, we identify the node. In this circuit, we have two nodes. So node 1, node 2. Next, we need to define the direction of the current in each branch. And we can define any directions we would like. I define I1 in this case, I2, I define I1 in this direction, and I2 in this direction, and IX is given. These two current sources, the direction is this direction and this direction. That's step 1. Next, step 2, we want to apply KCL for each node. At node 1, we have current flow into equals current flow out to. So current flow into, that's 2 and I1 and I2. And KCL at node 2, current flow into, that's I2 and 3, this current source, current flow out to, that's IX. And here I use a small IX here instead of a big IX. They're the same thing in this case. Now we obtain two equations, equation 1 and equation 2. But we have how many unknown variables? I1, I2, and IX. So 3 unknowns, 2 equations, we cannot solve it. Next, we want to apply Ohm's law. We want to express all these currents as a function of nodal voltage. The nodal voltage at node 1, I call it V1. The nodal voltage at node 2 is V2. We know V1, the sign of V1 defined this way. I1 flow into this direction. This setup agree with the sign of convention. We can apply Ohm's law with positive sign here. So I1 equals V1 divided by 10. What is I2? I2, that's the current flow in this branch. We know that VR, the voltage across this resistor, that equals V1 minus V2. So what is I2? V1 minus V2 divided by 10. And this is 10 ohm here. What is IX? IX, that's the current flow into this branch, that equals V2 divided by 20. That's a 20 ohm here. Now we plug in all of this I1, I2, and IX into equation 1 and equation 2. I1 equals V1 divided by 10. I2 equals 2, that's this term, and equals to 2, that's 2 here. Look at this equation 2. IX equals to V2 divided by 20 here, and then minus I2. So I move I2 and move into right-hand side of the equation. That's minus V1 minus V2 divided by 10. That's I2. And this equals to 3. Now, if we look at this two equation here, this equation 1 and equation 2 becomes a function of V1 and V2. We have two unknowns, two equations. We can solve V1 and V2. So we want to use matrix. So this is a general format of two equations with two unknowns, x1 and x2. We know that this constant here, b1 and b2, that's a b vector. We know this equation can be written at ax equals to b. A is a matrix of 2 by 2. X is a vector of 2 by 1. And b is a vector 2 by 1. Elements of matrix A, that's A11, A12, A21, A22. That's the coefficient of x1 and x2 here in these two equations. And then using software, either MATLAB or octave, we can solve this vector of x1 and x2 that's equals A inverse multiplied by B. To solve this circuit, we only need to fill out the element of matrix A. In this case, the unknowns are variable V1 and V2. Write it here. The coefficient of V1 from this equation is 1/10 plus 1/10 here. The coefficient of V2, that's minus 1/10. And let's look at the second equation. The coefficient of V1 is minus 1/10. It's coming from this term. And then for the coefficient of V2, that's 1/20. It's coming from this term and this term, but there is a negative, that's a plus. And this is the coefficient of B, and 2 and 3. We write in here, and we can solve V1 and V2. After we obtain V1 and V2, we can use the information of V2, we can obtain Ix.